I heard from a couple of people about installing R, and it'll be good if the others also try to install R in our studio in the next few days, because the next week I plan to get to just starting R. And so if you can do the installation instructions that I sent out in my email, and also, of course, the file online. And then what I would like you to do is to copy the console output. Don't take a screenshot. Copy the console output and send it to me. And we'll see, if I need to help somebody, I can do that before next week. Okay, so then we're going to continue with, we just started Excel last week, and we're going to continue with that now. So the simple question we're going to ask, just to work as a way to learn to do stuff in Excel, is what happens if you change the scale? So typically in our work, we get lipid measurements in milligrams per deciliter, but some journals want them in millimolar or nanomolar terms. So suppose you have all your data, you've analyzed, and now you have to change the units. So what does it mean? Do you have to redo your means and standard deviations and so on? Or can you just convert the means and standard deviations you got before? So that's what we're going to look at. So again, as I said, it's not that I care about units or anything. It just is a way to learn some little things in Excel. So I want you to work on the second tab of the data file that you all have. And so the question, as I said, is what happens to summary stats like mean, standard deviations, and so on when you change units? So that's what, and also along the way, some simple normality checks. I think I mentioned a couple of things already last week, and so I'm just going to repeat that. Now, just to be clear, once we learn R, normality tests can be done, rigorously there. But so just, as you're collecting your data, it'll be nice for you to check things. Okay, so the first thing is, this has already been done, but I just want to tell you how to do it in case you don't know. Often you don't want the top row of your spreadsheet to be scrolling off when you scroll down, looking at the data or working with data. And so the way you do that is, there are two different views. Say in Windows, you would click on View and Freeze Pane, and then do the freeze top row or freeze first column, and so on. And this has already been done in the file you have. And on a Mac, it may be slightly different or not. Okay. So first, what we want to do is, I want to create a blank column next to the total cholesterol column. So it's very simple. You go to the top of the next column, say C here, do a right click. I can never remember what I'm supposed to say on a Mac. So you do a right click and you say Insert. And if you click on Insert, you should see a blank column showing up. Again, if people have any difficulty with any of this, you should send a direct chat, not a chat to everybody, but a direct chat to Isabella, Nidhi, or Karina. Okay, so now we want to do the conversion. These are milligrams per deciliter, and we want to convert them to millimolar terms. And so you can say the column here equals 217.7 divided by 38.67. That's the conversion factor. But a better way to do it is to use a symbol. That is, you say equal B2. Okay, this is column B, row 2, equal B2 /38.67. we did some of this last week, so nothing new here. And so when you do that, you get 5.6. So those are the total cholesterol for the first subject in millimolar terms. So next step we haven't done before, and that is we now want this formula to be applied to all the subjects. And the way you do that, I remember, I think last week I said, hover your cursor and then copy. So here, you're going to hover your cursor until this becomes a plus sign. And instead of copying, dragging down, you can just do a double click. If you do a double click, Excel says, this person wants to copy this formula as far as possible. So it'll look at this column and say, okay, I'm going to copy it as long as there are data in this column. So that's what you should see. When you do that, you should see numbers going all the way down to row 86. Okay, so now this may be just a rehash of what we did last week, and it may be boring, but let's just do it quickly. So you say we want to get the mean of all these values. So you say equals average B2 colon B86, right? Similar to what we did last week. And so B2 to B86 is the range of all the cholesterols here. Now, one reason I'm doing this here is that there is a slightly different way to do it, which some people prefer, but not my preference, but some people prefer to do it that way. And that is, you say equals average, but you don't say B2 or B86. Instead, you just highlight the data. So if you say average open paren, and then you just highlight all the data that you want averaged, Excel will fill in B2 colon B86. And it'll also close the parenthesis when you hit enter. So that's it. And and you can do standard deviation the same way, equal to STDEV, open paren, and then highlight the range, or you can type B2 colon B86. Whatever, works you. What I'm showing you today, nothing new here. You can Google and learn everything. Right. Okay. So this is something new. We didn't do this last week. And this is something that I think is very useful to calculate even in Excel as a way to check normality. So this is called and even otherwise, it's a very useful statistic to summarize your data with. So you say coefficient of variation, and the coefficient of variation is simply standard deviation divided by the mean. So that's what this formula is. It's B89 over B88, and then we multiply by 100 so that we can talk about it in percentage terms. So what is nice about the coefficient of variation is that it has no units. It doesn't matter whether you express your data, we'll see presently, whether you express your data in millimolar terms or milligrams per deciliter, or what it is you're looking at. Totally different types of data. You can still say how variable are the data, and you can express it as a coefficient of variation. So it could be some measure of the precision with which your instrument works, or it could be a measure of how much variability there is between people, or replicates, or whatever. And the coefficient of variation expresses something in a dimensionless, unitless way. And so it's easy to evaluate that value. So that's what the coefficient of variation is. And it's a very, very useful thing to summarize your data with. And I think we did this last week. So the percentile, you can say quartile, comma 1, B2 to B86, comma 1. The 70th percentile is B2 to B86, comma 3. And I just have a different way of doing median here. You can just say median B2 to B86, or you can also say quartile, second quartile. and number 2, and the end of the second quartile. So this is just I have the formula here just to reinforce in you that the median is the same as the the end of the second quartile. Okay. So I trust people have done these formulas, and I have some very crude normality tests that I do in Excel. Just to be very clear, when you start using R, there are formal normality tests which will give you p-values to say whether the data you have satisfy the normal distribution or not. But in Excel, you don't have those tests. So these are my, my rules of thumb or whatever to, check for normality as you're collecting data. So one question to ask right away is the coefficient of variation too big? Now, the reason is that the coefficient of variation tells you how big the standard deviation is in relation to the mean. Now, mostly in biology, we have data that are positive. We don't have negative values by and large. And so that means that if the standard deviation is, say, half of the mean, then that means that if you start at the mean and you go down 2 standard deviation, you're at 0. Now, we saw last week that plus minus 2 standard deviation include about 95% of the population. But you still have some values outside of 2 standard deviation. You could have. But if you hit coefficient of variation that's close to half the mean, then you don't have any room there for low values. And that usually happens because you have a skewed distribution where you have some very large values. And that results in the standard deviation being calculated as too big, as large. And so that's a hint. So if you find the coefficient of variation is large, like for instance, more than 40% in data that are all positive, then it's likely that you have a skewed distribution, which is not normal. And likewise, if you have a skewed distribution, the mean is going to be bigger than the median. And finally, if you have a skewed distribution, not symmetric, I think I mentioned this last week, the median won't be midway between the 25th and 75th percentile. That's it. And this is a further thing that you could do that I'm not interested in talking to you about, because just do the tests in R. I think these 3 are very helpful, because as you're going along, you can calculate mean, standard deviation, coefficient of variation, and the quartiles. And once you do that, you can say, well, how far is the mean from the median? So let me take the difference and divide by the standard deviation. That is, express the difference again in unitless, dimensionless terms. And you can say, how far is the mean from the median? And then you can ask, what about the spacing from the median to the 75th percentile and the 25th percentile to the median? How do they compare? So you can look at that ratio. And so this is what I would like you to do with your own data. That is, look at the coefficient of variation, see how far the mean is from the median, and how far whether it's symmetric with respect to the quartiles. These are very simple tests to do, and it's good to just get into the habit of doing them routinely, especially when you collect new data. So that's what we have done here. And now I'm going to show you, I don't think we did that last week. You can copy formulas and so on, not just from one row to the next, but also from one column to the next. So we did all these calculations for total cholesterol, but you can do the same thing by hovering the cursor till this little square becomes a plus sign, and then drag across. And if you do that, Excel now will do the same calculations that you did for total cholesterol in milligrams per deciliter. It will do that for the other variables as well. And just to finish off what we started with, I claim the reason I wanted to do this was to see what the effect of changing units is. When we went from milligram per deciliter and divided by whatever that number was, about 38.67, to get millimolar terms, you can verify now that if you take each of these values, mean, standard deviation, quartile, and you divide them by 38.67, you will get the values here. That's one little observation. And the other is to note that coefficient of variation didn't change. As I mentioned before, it has no dimensions, no units. So whether it doesn't matter whether you express total cholesterol and milligrams per deciliter or millimolar terms, you get the same value. And likewise, these simple normality tests. Okay, so that is one thing I wanted to say. And the other, not so, I'm not interested in dwelling on it at all. You can see, like for instance, in our work, we know from long experience, triglycerides are not normally distributed. Because most of us have triglyceride levels below 100, but then there are people who have 300, 400, and so on. And so it's a skewed distribution. And similarly for Lp(a). These are skewed distributions, and so you can see that they are not symmetric. Right? Instead of having a ratio of 1, they have higher values. So that so when you have a situation like this, you should consider finding out. Like for instance, in our work, we routinely take the log of triglycerides to analyze, and we take the square root of Lp(a) to do the analysis, because we find that the log of triglyceride and the square root of Lp(a) are closer to a normal distribution than the untransformed values. Okay. So this is just some description of skew and kurtosis. I'm going to skip that part because I'm really interested in you're doing normality tests in R. And R will also do the skew kurtosis statistics. Okay. So I want to spend some time talking about the standard error of the mean. Would anybody like to, this is something that you see a lot. You see in papers, they report the mean and standard error. So what do they mean by the standard error? Does anyone want to speak up? So go ahead, Zach.
So right now we're working with a sample, and when you want to try to figure out your sample's mean compared to the population's mean, the thing with in a smaller sample, you're going to have more variability, and to take that into consideration, if you want to try to calculate what the mean of would be in the population based on your sample that you're working with, you take the number, the n, the participants, if you will, or the values, and you would take the standard deviation you've calculated and divide it by the square root of the number of data values you have.
Right. Absolutely. Absolutely. Thank you, Zach. So I have a question on the slide there, Zach or anyone else. So Zach expressed it very well. When the sample size is small, there's going to be the mean that you get from the sample is not going to be not necessarily that close to the population mean, and so the standard error expresses that uncertainty. So what would the standard error be, Zach, if the sample size is 1?
It would be the same as whatever you calculated as your standard deviation.
Right. You haven't calculated whatever the population standard deviation is. That's what it will be. And as Zach implied, as the sample size increases, this uncertainty decreases. And and Zach told us, I think, it's a standard deviation divided by the square root of n. And that's why it comes out very naturally that if n is 1, SEM is just a standard deviation. So why square root of n? I'm not going to spend time on it, but you can show fairly easily that when you add variables to get the average, the variances add up, not the standard deviation. And so then when you take the average, the variances add up, and then you get the standard deviation by taking the square root of that. So you end up with a square root of n in the denominator. So, okay. And so I want people to have a feel for what Zach said. And that is Zach's comment being that as the sample size increases, the standard error goes down. So I would like you to work in the third tab. And so I have 80 values in the first column. So I want you to imagine that those 80 values, they are the 80 individual values from 80 subjects. They're the same data as in the previous tab. I just have 80 in order to have a round number. But you can think of those 80 as 80 samples of size 1. That is, each subject you just that's the whole sample. And then I want you to think of the second column, which we haven't calculated yet, as 20 samples, each with 4 subjects. And the third column would be 5 samples, each with 16 subjects. So it's not that you're actually going to analyze your data this way, but this is just to, I'm trying to have a couple of ways in which people can get comfortable with what Zach was talking about. And okay, so you already have in column B you have the 80 individual values. So now I want you to take the first 4 subjects, consider them as a sample. And so this sample has a mean, which you can calculate with this formula, equals average B2 to B5. Okay, I trust people get that. And so then comes a little trick that I learned from a student a while ago, and that is, in order to propagate this formula every 4, that is, I want to view now in column C, I want to view the data as being 20 samples of each with 4 subjects. So that means I want to get the average of these 4, and then the next 4, and the next 4, and so on. And it turns out I don't have to copy this formula over and over, copy and paste. Instead, what I can do is I can highlight not one cell, but the 4 cells. So you highlight the 4 cells, and then you do this double clicking again. So if you do that, what you will find is that Excel will copy this as it goes. That is 3 blank cells and an average, 3 blank cells and an average. So this is what you should see with the formula and the double click. Okay, so I trust people have that. So this simulation or the pretense here is that column B has 80 samples of 1 subject each. Column C has 20 samples of 4 subjects each. Each sample has a mean here. We know all the mean. Now we do the same thing in column D, except that now we want to consider 16 subjects. So you enter this formula in cell D17. You say equals average B2 to B17. And when you do that, you should get 201.3. And now you do the same thing that you did in C, that is highlight these 16 cells and then double click. Okay, so you should get these, that is like 198.9 here is the average of these 16 subjects, just as 214.8 is the average of these 4 subjects. And 175.3 is just the average of 1 subject. Okay, so now the purpose in this exercise is to see what happens. You know, Zach was talking about how the mean may vary more when the sample size is small. And that's the point I want you to get here. So we're going to do that by simply calculating the standard deviation of these values. That's all. So you say equals STDev B2 to B81. And when you do that, you get 31.9. And then I would like you to drag that across, and now you get the standard deviations of these columns, these numbers and these numbers. So a couple of comments here. One, just a passing comment. I think we saw that last week. When you tell Excel to average B2 to B81, there are values in all the cells. But in C2 to C81, there aren't values that, you know, there are only 16 values or something like that, or 20 values. But Excel knows to ignore all the blank spaces. So it actually, this is the average of these, this is the standard deviation just of these 20 numbers, not the blanks. And likewise here, this is the standard deviation of the 5 values. Okay. So what do we see here? What we see here is that the standard deviation goes down. That is, the variability of the means is going down. That's what the standard deviation is. Each of these standard deviations shows you how much the mean is varying from sample to sample. In this case, the mean is not varying much from sample to sample. It has a standard deviation of just 7.9. Here, the mean is varying more from sample to sample because each sample has only 4 subjects, not 16 subjects. And here, of course, each sample has only 1 subject, and the variability is much, much more. So I don't know that this is particularly helpful, but I found it somewhat helpful in understanding why the standard error goes down as the sample size increases. Because as the sample size increases, the means are much more stable. They don't change so much from sample to sample. Okay. So now I just have one final way to think of what happens in when you do standard error as the sample size increases. So this is a normal distribution, and let's say I have 8 values drawn at random from this distribution. So you can see the mean is here, and the values are sort of distributed around the mean. So these are my individual values. So you're not doing any calculations here, just looking at the picture. Now, so that is 8 individual values. Now suppose I look at the average of these 2 at a time. Okay, so I have the first two values and an average for that. I have the next two values and average for that. I have the next two values and average for that. And another two values and average for that. So what you see here is that, I think this is a point that Zach was making, that the white stars are closer together than the little yellow stars. That's what happens when you take an average of two values at a time instead of just looking at individual values. And you can see why. If one value is far from the mean, maybe the other value won't be so far from the mean. So the average tends to be closer to the mean. And that's what you see here. The white stars are closer to each other and to the mean. Now think of these 8 stars as looking at them 4 at a time. So you have 4 little yellow stars, and with the 2 white stars, and a big yellow star is the average of these 4. And I can take the next 4 values and get the average of those 4. So what you see here is just as the white stars were closer to each other, one another, than the little yellow stars, the 2 big yellow stars are even closer to each other. And this is what happens with increasing sample size. The standard deviation of the little yellow star is bigger than the standard deviation of the white star, and that is bigger than the standard deviation of the big yellow star. And this is what happens with the standard error of the mean. The standard error of the mean conveys this, that as the sample size increases, you have greater confidence in the sample mean. And so you can show theoretically this thing that I showed you before. So, so to go back to the calculations you did, what is called standard deviation here is actually the standard error of the mean for n for 1, 4, and 16. And so for sample size 1, the standard error was 32. For sample size 4, it was 14.5. And 16 was 7.9. So what we see here, in fact, is this formula holding good. Because if this is the standard deviation, the size 4, you expect the standard error to be 1/2 square root of 4. And when it's sample size 16, you expect the standard error to be 1/4 of the standard deviation, or the value here. And that's what we see. Okay, so I'm done with this, okay, so are there any questions? This is the second part of my slides, lecture slides. Okay, so so this section I want to talk about correlation coefficients. Before we get to correlation coefficient, correlation is something broader and relating to association. And so, for instance, when we do a t-test and find a significant association between x and y, we conclude that x and y are correlated, possibly causally. So I just want to get one little thing out of the way. And it's a little bit early for me to be showing a video, but I'm going to do that. Okay, I trust people hear the sound now.
Science Goes to the Movies, a look at the stories of science and how they change our culture. I'm Faith Saley, and the Ice Age franchise is all about prehistoric animals, and of course they're ignorant about a ton of things, and appropriately, they continually mangle a very basic scientific rule. Correlation does not imply causation. Without that rule, do you think we would be, stuck in a scientific ice age?
Well, so I think that sentence has been given more weight than it deserves, if I may.
You may.
It is true that correlation does not require causation. But almost everything in this world that is correlated
Is causal?
is causal. Almost everything. So we shouldn't be shocked if someone wants to infer causation and ultimately learn that it's not. Almost everything is causal. You flick a switch, the light turns on. You put one foot in front of another, you move forward. Friction propels you forward. You press the gas pedal, the car accelerates.
Okay, you're coming up with a whole bunch of scientific examples that are undeniable. But I'm thinking of
thick
dangerous
cumulus
ones.
clouds, rain comes out of
What about
them.
when people use them for social things and things that turn into racism, like a disproportionate number of people of color end up in jail and they grow up in a certain place. Then you say, oh, you grew up in this city, you're going to be a criminal. Right?
Right.
That kind of application of correlation.
No, so the way you should say that is.
So if people are interested, I have longer version of that video, and I think it should be available on YouTube freely. And the point is just that people are taught that correlation doesn't imply causation, and that is true. It is true. It's a truism. In my view, correlation demands an explanation. And so anyway, so Neil deGrasse Tyson was talking about that aspect of correlation and causation, and so I don't want to get away from I'm always conscious of the point that Tyson is making, that when you have a correlation, you need to explain it. You can't just say, oh, it doesn't imply causation. And okay, but this unit right now is just about correlation coefficients, not the broader meaning of correlation. So I should also say I don't use correlation coefficients very much myself, because I think there is a particular problem in interpreting correlation coefficients that I'll get to, but you have to know how to calculate them. So if we did a scatter plot of y versus x, suppose you do a scatter plot, and you have a zero correlation, and what does that mean? What would the scatter plot look like? Like if you did a scatter plot and you fitted a line to the y versus x thing and you had zero correlation, what would the line look like? Would anyone like to say?
It'd be flat and all the points would be scattered all over the place. No pattern.
Right. Okay. So the key point that Zach makes is that the line would be flat, horizontal. Okay, good. So what would the line and the points look like if the correlation is +1?
Okay, so it'd be a diagonal going at 45 degrees from the bottom left, going upward to the upper right.
Well, no. See, but one thing to keep in mind is that the correlation can be between variables that are completely, different units and so on. So what you said would be correct if you had two ways of measuring the same thing, and you say if they're perfectly correlated, then that line would be a diagonal. But it could be, the two variables don't have to be measuring the same thing; they could just be perfectly correlated. Right? And it doesn't have to be a one-to-one thing. Take, for example, suppose you said somebody's leg length is a fraction of their total height. So if you did a correlation of height versus leg length, there will be a correlation, but it's not necessarily a diagonal line. And also, where would the points be in relation to the line? You said before for zero correlation, points would be all over the place.
The points would essentially be slowly moving, so let's just pretend you have like 0 all the way on the left on the x-axis,
right?
And then higher values. The points would be kind of looking like they're walking their way up across the graph. So
right, but so where would the points be in relation to the line?
They'd be on both sides.
They'd be perfectly on the line.
Anyone else want to disagree with Zach?
Doesn't it mean like perfectly fitted to the line if it's 1?
That's right. That's right. Yeah. So that is, the points would all fall right on the line. So Zach, what you said is correct for a positive correlation. But here I'm asking for a correlation of 1. So that means that the points will actually be on the line. The line will be going up, as you said before, because it's a positive correlation. But 1 means the points will fall on the line. So the next question is, what about an R of -1?
Oh, let me redeem myself on this one. So it's a straight line.
I've written you off already.
So all the points would be on the line, and it's going from the top left to the bottom right.
Right. But the line will be going down as x increases, and it'll do okay. So how about 1.5?
I think the range of correlation coefficient is from -1 to 1, so that's not a possible value.
Not possible. Yeah, that's right. Nadia is correct. It's not possible to have a correlation coefficient of 1.5. And finally, this is the hard part. What does the correlation coefficient of 0.5 mean? This is where the interpretation of the correlation coefficient comes in. So it's easy to interpret the correlation coefficient of 0 or 1 or -1. But when you have some value in between, what does it mean? So we'll try to see if I can make if I can help with that or not. So I have some pictures I stole off the web, and the correlation coefficient expresses, this is how I want to understand it, how small these distances are of the points from the line. But it says how small they are in relation to the starting variability in the y. So you look at all these residuals and you say, how do they compare with the overall variability in y? And the correlation coefficient conveys that. So this is maybe a slightly more formal way of looking at it. Say these are, you have a bunch of data and this is the fitted line. And let's say the mean of all your y's, I'm not showing the y's here, the mean of all the y's is here, y mean. So now all the individual points, their variability around this mean, that's what you start off with, your starting standard deviation. Now, once you have the line, you can say this total, this big distance of the point from the mean can be split into what the line explains, because the line says, really, this is my good guess, prediction for what the y should be. You have what the line predicts, and then you have what the line doesn't explain, which is called the residual. So you're breaking up this big deviation into what the line explains and what the line doesn't explain. So the R squared is just 1 minus what the line doesn't explain and what the total variability is. So that's what the R-squared does. It is telling you how much of the total variability has been explained. So I'm sorry, I have another cartoon here, vaguely related to correlation causation. And so to go back to R squared, a formal way of saying it, how much of the variance have you explained? So you take the residual variance and you divide that by the initial variance and 1 minus that. So if the residual variance is 0, then correlation R squared is 1. So R is either plus 1 or minus 1. If the residual variance equals the initial variance, that means you didn't explain anything, then this will be 1 and the R squared will be 0. So this is what we talked about at the beginning, how to interpret. So if you have something in between, this is the formula. So the problem that I have with the correlation coefficient is that it doesn't actually tell you what the residual variance is. It tells you how small the residual variance is in relation to the initial variance. So if you have 2 sets of data from different sources, then the residual variance, it can be the same in the 2, but the R squared may appear different depending on the initial variance. So if you have data that show a lot of variability, then R squared is going to look good when you fit a line through the data. If your data don't have much variability, the line may be just as good, but the R squared won't look so good. So that is my problem with R squared. But anyway, so we're going to just go through again, folks. There's nothing, I'm not saying anything new here. These are things that even if you didn't know, you can Google and learn. So, but anyway, so we're going to work in the 5th tab. It's called MET. We're going to make a scatter plot of triglyceride versus total cholesterol. And along the way, I will try to make the point that a higher correlation coefficient doesn't necessarily mean a smaller error. Okay. So I would first like you to just, it's a very simple command. And so I'm interested in sorting the data so that the triglyceride levels they go from low to high. Now, it's a very simple way to do that in Excel. You just pick any cell at all in the TG column, and you go up to Data, and you click on A to Z, sort, and that's it. Not the sort icon, but just A to Z. If you do that, there is Excel doesn't ask you. It assumes that you want the data sorted by this column, and that's it. So you'll notice that when it sorts the data, it doesn't sort for one thing, it doesn't sort the heading. It recognizes that there is a header, so it doesn't sort that line. And it also doesn't sort these columns over here, because it assumes once it hits a blank column that these are the data to be sorted. So, but anyway, you may want to be careful when you use this feature. It may be safer to select the entire range and go through a dialog to sort. Anyway, we've got the data sorted. So next, I just want you to select columns A and B, highlight AB, and then do an insert scatter plot. That's what I would like you to do. And in Windows, it's very similar. So you click insert, and then there is some icon that looks like a scatter plot. and then so I have the two screenshots depending on what people have, whether Mac or Windows. And so once you do that, you should get the scatter plot. So this is what you get. So I'm just going to spend a little bit of time on cleaning this up. And you can see that the axes start at 0, but in fact people don't have total triglycerides or total cholesterol close to 0. So you may want the axes to start at some positive value, and maybe you want to get rid of the grid line. So I'm just going to show you how that gets done. So so you right-click along the axis, along the x-axis, and to highlight that axis. And when you do that, these would be the options that will come up, and you can say format axis, and that will allow you to choose the starting value for the x-axis and so on. So you will see some interface like this. This may be some older Macs, I'm not sure. This is Windows and possibly newer Macs. And so I want to start at 130 and go up to 300. So I do that. And this is not important, by the way. I mean, it doesn't matter if you don't do this at all. And so you can see now the x-axis goes from 130 to 300. And you can do the same thing on the y-axis. Right-click on the y-axis and format axis. And then I want to go from 50 to 550. And and then I can click on any grid line and then delete the grid line. Okay. So this is what I have. So finally, we want to add a trend line. Basically fit a line through the data. And that's very easy. You just right-click on any data point and you say add trend line. And that will, and then you need to, this will be set automatically. The key thing that you need to do is these two checkboxes have to be turned on. Display equation, display R squared. And when you close it, you should get the equation. You should get this equation and the R squared. And the only thing is that it'll maybe lost in the points here, but you can drag it away from the points easily enough. So what does this mean? What does 1.5537 mean? Basically it says if total cholesterol goes up by 1 milligram per deciliter, triglyceride goes up by 1.5537 milligram per deciliter. So that's what it means. Or if total cholesterol goes up by 10 milligrams per deciliter, triglyceride will go up by 15 point something. Notice that the R squared is 0.31 here. And so I'm going to skip this part, and there's nothing very original here. I'm just going to cut to the chase. What I'm doing here, but you can go through it later in your own time. Basically, the one reason I had you sort the data by triglyceride is I want to say, suppose I take the same data, but look only at the range 90 to 120. Okay. If I do that, I would highlight this part and do a scatter plot and go through and get R squared. So what you see here, these data points are all to be found here. Okay, that is in this range 90 to this. All the points in this range are found here. Now, so this line can't be any worse than this line. But the R squared is much worse. Here the R squared is 0.31, and here the R squared is 0.1. And that's all the point I want to make, that the same data, when part of a much wider variation, you're going to get a good R squared, but not if you just look at a narrow range. And this is calculated here. You can do these you can put these numbers in if you like. The formulas here are already pre-entered. So you should be able to just enter the 0.31 and 0.099, and you will see these numbers show up. And what this is saying is that all the data, the residual error, that is the scatter of the points around the line, is 73. There is 73 milligram per deciliter variability. Now, when you in the small graph, the residual error is only 8.6. So if you want to think of which line has a smaller residual error, there's no comparison. But if you are asking which line explains more of the variability, 87.9 and 9, it turns out this does a better job. So this is, my point here is you need to be clear. R squared is giving you some information, and the residual error, that is what is left unexplained by the line, gives you different information. So depending on the problem, you may want to look at one or the other or both, depending on your situation. Okay, so right, and so can we use both R squared and residual error to determine fit quality of so the residual error tells us the fit quality, that's it. But R squared is okay if we compare different models fitted to the same Y. We'll do this when we get to R and when we consider different models for the same data. There, the R squared is entirely appropriate. Because if the raw standard deviation is the same, the R squared is bigger if the residual is smaller. So the problem really comes with R squared only when you have different sets of data. So for instance, if you have your own data and you get some R squared for some relationship, and you look at the literature and people are reporting other values for R squared, before you get excited or upset, you should look at the range of values in the publication as opposed to yourself. So if your range is narrower, then you shouldn't expect the same R squared that you see in the literature. So that's what I want to get to. So with two different data sets, R squared doesn't help. Okay, so I'm also going to skip this part because this is again some detail of how to do something in Excel. And basically, if you say you wanted to graph HDL and BMI, you notice they are not adjacent. What I showed you was just TC and TG, they were adjacent. So everything fell into place easily. But if you want to graph HDL versus BMI, it gets to be more complicated. So the way I have found is you go with the Y variable. Let's say I want HDL on the Y-axis. And so you just pick C and D. Just pick whatever variable is next to that Y variable and make a graph. Now this is actually giving you HDL versus TG. Now you edit this graph and say, instead of TG, use BMI. So that's what you have to do. And that is sort of explained in this. And I don't want to spend time on this. And if you try it and you have some difficulty, you can email me or you can Google and learn it much better. I myself learned this by Googling. And yeah, so I've tried to make this clear. And then you can label the axes. Maybe we'll do that. But you have to work in the chart design on a Mac, and in Windows, you work under chart tools and layout, and then you can go through and pick the axes options and do it. You can just place the cursor in boxes and edit the titles. So, and the same thing, it's a little bit more messy for the y-axis, and you can do it. And finally for the title. So you can make a graph like this with some axes labels, and which are not given in the Excel spreadsheet, and a title that you want. Okay, so I think I'm done with correlation. Okay. So okay, and so we are going to do learn to do paired and unpaired T's, and so I want to do all this in just using one data set. So this is a paper we published now 30 years ago, and so I will describe the design of the study in a minute, and so we're going to do some t-test analyses in Excel, and then when we switch to R, we will actually start with the same data set and do learn to do ANOVAs and analysis of covariance and so on using the same data set. Also, we will do non-parametric tests. Okay, so this was the study design. So we had 36 subjects who were all basically medical students living in the dorm here, Bard Hall, and we put them all on a so-called average American diet. It's sort of this high-fat American diet. About 38% of the calories is fat. And so we put them all on that diet for 10 weeks. At the end of the 10 weeks, they were randomized into one of three groups. 12 of them stayed on that same awful diet. 12 switched to a mono-enriched diet. The fat content was similar, but it was monounsaturated fat. And 12 of them switched to what then was a recommendation from the American Heart Association for people interested in lowering their lipid levels. So this was to 30% calories is fat diet. It's called the step 1 diet. So this is the basic design. So everyone studied at a baseline conditions on a standard diet, and then switched to one of three, either stay on the diet or switch to one of the other two diets. This was the study design, and measurements were made 3 times on each in each phase, and we're just going to be looking at the averages of those 3 values. Okay. So in Excel, we're just going to look at 2 diets first, 2 diets at a time, not all 3 diets. So we have 12 subjects in each diet group. How do we utilize the crossover aspect of the study design? And how do we use the third group? We won't use the third group until we get to R. Okay, just, I don't know if this helps or not. So we are first going to do a paired T in the mono diet. So let's just talk about the AAD subjects. 12 of them stayed on the same diet. And we had the mono subjects who switched from AAD to mono. And so the first thing we're going to do is it's a paired t-test comparing the mono to the baseline to the study value. Okay. Then we're going to do an unpaired T comparing the change in mono with whatever happened on the AAD. So these are the two types of comparison, and I'll talk a little bit, or maybe a lot, about why this unpaired test is so important. Basically, the paired test doesn't control for time. So you have to control for time. Maybe things change with the season or just being on a study and so on. So that's why it's important to have a control group, and you look at the change in your intervention group with whatever happened in the control group. Okay. So we're going to be working in a tab that's marked NEJM. So here is a slight variation on freezing the top row. I actually have two rows here that are like header lines. So we want those two lines not to scroll off. And so the way to do that is you don't just say freeze top row. You put your cursor, click on the first cell in row. Again, you don't have to do this. It's already been done. You click on the first cell in row 3, and then you say view and freeze panes, and that'll make sure that the top 2 rows don't scroll off. But as I said, this has been done already. Okay, now just to for people to have an overview of the data, there are baseline values, 3 lipids, total cholesterol, triglycerides, and HDL. And this identifies what diet the person was on. And these were the study values. And these have already been calculated for you. That is the TC change. It went from 208.3 to 212.3 in this subject. So the change was 4 milligrams per deciliter. And so that has already been done for all the lipids, for all the subjects. And for now, just ignore column A and LM. Those are made up variables that I have there just to have something to do in R, to look at some complicated things in R. So the basic data are just in columns B through K. And that's what we're going to be working with here in Excel. So I already have set up a table on the right. And so the next step is for you all to enter formulas in there to calculate stuff. So we first do an average. This is a summary for the first group. You notice that I've arranged the data so that the 12 AAD subjects are together, 12 mono subjects are together, and so on. So we're first going to summarize the data for AAD. So what is the initial starting value? Starting mean is the average of B3 to B14. So that's what you do there. And so once you've done that, you can do the standard deviation the same way, ST-dev, whatever. And then once you've finished with the initial mean standard deviation, you do the final mean and standard deviation. So that is, final mean would be average of F3 to F14, and the standard deviation would be ST-dev of F3 to F14. So finally, the change. So the change is going to be this minus 1.9 you're going to get by doing average of I3 to I14, and then ST-dev of I3 to I14. So once you've summarized everything for total cholesterol, as we saw before, earlier in another tab, you can just highlight these 6 things and just drag across, and you will have the summaries for triglyceride and HDL cholesterol. So something to remember here is this worked. My dragging across and getting the summaries for triglyceride and HDL cholesterol worked only because I had organized the data that way. That is, the starting values were consecutive columns, the study values for consecutive columns, and the changes for consecutive columns. And because of that, these formulas could be copied over easily. So if I didn't have them in consecutive columns like that, the formulas couldn't be carried over, copied over so easily, readily. Okay. So you now have the summary for the AAD subjects. Now we want to copy this to the other two diets. So we copy that summary that was highlighted. So you copy and then you paste it in the mono entries and in the step 1 part. So now you will get the summary for all 3 diets. So it wasn't hard work at all. So you didn't have to retype the formulas, everything. Now, again, the reason this worked, I should say, is that we had exactly 12 subjects in each group. And because of that, when we copy the formulas from the AAD to mono and then to step 1, it worked because they had the same number of subjects. If they didn't have the same number of subjects, after you copied, you would have to edit the value. Okay, so we now have the summaries for all the 3 groups, and we're ready to do t-test now. So it's pretty easy. As I mentioned at the outset, we're first going to do a t-test in the mono group, comparing the starting value to the study value. And the way you do that is you go to that cell, which is marked pair T, and you say equals. You can copy paste this if you want, or you can just type it as you have it here, as I have it here. You say equals t.test. That's to do the t-test. You give the starting range, that B15 to B26, and then you have the ending range, F15 to F26. Okay, and then these are magic numbers. I mean, they don't necessarily make sense, but as you're typing, Excel will sort of tell you what to expect. So 2 is for a two-tailed test, and 1 is for a paired test. I showed this screenshot here. When you get to that 1, it says 1 is paired, 2 is unpaired, and so on. So you want to do, here we're doing a paired test, 2-1. We always do two-tailed tests. We don't do one-tailed tests. If anyone does a one-tailed test, I get very suspicious that they're trying to spin their data. And the reason really is that in biology, in medicine, life is full of surprises. You may have a hypothesis, but it turns out the hypothesis is totally wrong. And I was, discussing the famous Women's Health Initiative study with residents yesterday. And so the dogma everybody believed through the 90s was that hormone replacement was good for the heart, for the woman, for a postmenopausal woman. That was what everybody believed. There was no question. And so they did a randomized trial. Now, they could have started the randomized trial by saying, we just want to see if HRT is better. We know that it cannot be worse. But if they had done that, they would not have been able to tell the world that, in fact, HRT was bad for the heart in many postmenopausal women. So you have to be open to the possibility that what you're comparing, your intervention that you think is good, may actually be bad. And that means that you have to do a two-tailed test so that you can reject the null hypothesis, whether your one way or the other way. Okay, so I think that's my rant. Oh, there it is. I have it in words here. So a one-tailed test can only be justified if you're never interested in knowing if a treatment you expect to be better is actually worse, or in knowing if the difference between the two groups you expect to be positive is actually negative. If you say beforehand that you are never interested in these things, then you can do a one-tailed test. But biological data are full of surprises, so a one-tailed test should almost never be done. When I see one, I suspect spin. Okay, you have the paired T now. So this is the paired T, highly significant. Change in total cholesterol from starting value to the ending value within mono. But we also want to do, as I mentioned earlier, an unpaired T comparing the change in mono with the change in AAD. So that's what this is. So this is doing a T-test of I3 to I14. That was the change on the AAD diet. And I15 to I26, that's the change in the mono diet. So remember, in the paired study, we compared columns, in the same rows. But here is an unpaired comparison. We are comparing some rows at the top with some rows here. I3 to I14 is being compared with I15 to I26. And the magic numbers are slightly different. The first one is still 2. That's for the two-tailed test. The second 2 is to say do an unpaired t-test. Not a paired t-test, but an unpaired t-test. That's what number 2 is. And the dollar signs, I think I explained the dollar signs last time. The reason I have the dollar signs here is that I'm also interested in comparing the step 1. Remember, there was a third diet. I want to compare the third diet as well to the AAD. And so, so when I copy this formula down below, I don't want this changing. I want this to be still I3 to I14. So I have the dollar signs here. That's the point of the dollar sign. Okay. So, just a parenthetical comment here. I have had colleagues work with me, very nice people. They either because they didn't understand or they didn't want to understand. There are 2 unpaired t-tests you can do in Excel, assuming equal or unequal variance. And what they would do routinely is to try both and go with whichever gave the smaller p-value. So that is not right. So you need to test for equality of variance and then use the unequal only if that test is significant. So you can't do that test in Excel. We will do it in R. So in Excel, I like to do just equal variance. That's a standard unpaired t-test, and that's what people should do, in my view. Okay. So once you've done the paired and unpaired for total cholesterol, you can drag across for total triglycerides and HDL cholesterol. So you can see here some differences between the paired and unpaired. Now, the total cholesterol was highly significant by paired, not so significant. It's still pretty significant by unpaired. But triglycerides were significant by paired, but not by unpaired. So it does become important to understand why this would be happening. Because again, it's not uncommon to see papers where they do a study like what we have here, control group and intervention group, and then they would report just the paired analyses in the intervention group without doing a comparison unpaired. They might say, we also did a paired test in the control group and it wasn't significant, but that's not enough. you really have to do an unpaired test between the groups, your intervention group and the control group. I'll say more about that. So I want you to now just finish up the t-test. So highlight this part and go to and copy to step 1. And so once you do that, you have the results for both of the intervention diet compared to the control diet. So you can see here the HDL cholesterol change here is significant by paired, but not by unpaired. Same thing that we saw with triglycerides in the other in the mono case. So in all cases, with a significant or not, the unpaired is less significant. So I want people to have a clear idea of why that is. Why is that an unpaired test less significant than a paired test? If anyone has any thoughts on this, I would love to hear before I go into my explanation, because it's not necessarily my explanation is the best. People may have other ways that they have learned as to why the paired test is always more significant than the unpaired test, even you have two groups.
I think paired t-tests are just like more powerful because you eliminate like any variations between groups.
So Ikra, that's a very good point. Now, but that only applies to suppose in the study design we didn't have baseline data at all. We only had the final values, right? Now, if you just compare the final values of total cholesterol on the mono diet and the average American diet, they are not significantly different. And the reason is that people's cholesterol levels vary all over the place. So your diet effect is lost in this big variation. And that's where the point that you made becomes very relevant. That is, a paired test is going to be a lot more significant because now each person is their own control. And you're looking at the diet effect in that subject. So if every subject goes down a little bit, or most of the subjects go down at least a little bit on the mono diet, that paired analysis is going to be significant. Whereas a small drop is going to be lost if you just compare the final values between the mono and the AAD. So I believe that's the point you're making, and that is important, and I should have mentioned it. And that's the reason why we have baseline values. But the paired analysis doesn't control for time. So as I mentioned, maybe when you go from fall to winter, people's lipids drop. Or maybe just being in a study makes people lifestyle change. And so they eat better or their lipids go down. So, so you have to control for time somehow. And the way to do that is by having a group where no change was made. So now the point that you made doesn't quite apply because you are looking at the change in each person. That is, the unpaired analysis here is not just of the final value. It's of the changes in the intervention diet versus the changes in the control diet. Now, the control diet had hardly any change, like the total cholesterol changed by like 1 or 2 milligrams per deciliter. So then why should that make the comparison less significant? So that's what we're going to see next. I mean, it's not a very obvious sort of thing that people may have gone into before. So I want to first go through what the paired T does. So just to be very clear. So now you notice that the paired T formula is comparing two columns. So in what follows, I'm not asking you to do anything, just follow what's on the slides here. So I'm going to copy these two columns to a new place, and we will discuss what is going on here. So this is a step 1 group. It's the last 12 people, and these were the starting total cholesterol, and these were the final total cholesterol. And the paired T comparing these two has some p-value. The paired T seems to compare two columns of data, but it is actually looking just at the changes and asking if the mean change is different from 0. That's what actually happens in a paired T analysis. That is, it is looking at all the changes, mean, standard deviation, standard error, and asking, is this minus 14.2 significant? That's what the paired T is doing. You do the paired T by giving two columns, but it's actually doing this. So for instance, if you have a paired T formula, you can just change these numbers. If these don't change, you will still get the same p-value. Okay. So the change standard deviation is 10.3, and the standard error is about 3. So the minus 14.2 has a standard error of 3. And so the T statistic, you calculate minus 14.2 over 3, and it's a pretty big number, or pretty big negative number, minus 4.7, and that has a very small p-value, 306. Very nice. Now, what happens with the unpaired T? With the unpaired T, we have the changes in step 1, and we have the changes or the lack of change in AAD. Just to be clear, these are different subjects, so they are not paired. So we have 12 subjects on step 1 with a mean of minus 14.2, and we have 12 subjects on AAD with a mean of minus 1.9, very small. So the difference is still pretty close to the minus 14. We have minus 14.2, and the difference between the two groups is minus 12.3. But the problem is that the minus 12.3, you don't have as much confidence in it as you do in the minus 14.2. So the reason is that a standard error for this depends on the uncertainty in the minus 14.2 and also the uncertainty in minus 1.9. Because the minus 1.9 is not fixed. It's not, God-given. And so you can see here, the minus 1.9 is an average of pretty wide range of values. So we can't treat the minus 1.9 as something that is known perfectly. So we have to take that standard error of the minus 1.9 into account when we calculate the standard error for the minus 2.9. The formula is very simple. As I mentioned a long time ago, variances add up. So you square this and you square this and you add and you take the square root. So you take the square root of 3 squared and 4.1 squared and you get 5.1. So now the T statistic is, instead of minus 14.2 in relation to standard error of 3, it is minus 12.3 in relation to 5.1. So the standard error is quite a bit larger. And so the T statistic for the unpaired is much smaller even though the value is not very different, minus 14 and minus 12. So it becomes minus 2.4, which is much smaller than what we had here, 5.7. So, and the p-value is 0.23. So this is the reason unpaired t doesn't have as good a p-value as the paired t. So does that help? Because for me, it's very important that people are clear about the difference between paired and unpaired, what actually happens in a paired t-test, and why the paired t almost always has a better p-value than the unpaired. To get back to this, so the standard error for the minus 12.3 is 5.1, whereas the standard error for the paired t is just the 3. And that's the reason. So the standard error for the unpaired t is always going to be larger, making the unpaired t smaller and less significant. That's just life. So just another way to visualize this, when we get to R, we're going to be producing these graphs. So for now, just take the graph for granted. So what is happening here is that, so these are 95% confidence intervals on these means. So these 95% confidence intervals are way away from 0, and so these paired t's are highly significant. Okay. But the unpaired t is less significant. The reason is that this mean is being compared not with 0, but against not just this mean, but taking the confidence interval on this AAD mean into account. If the AAD data were based on hundreds of subjects with very tight confidence interval, then the unpaired would have worked out okay. But in practice, the AAD with the same number of subjects as the step 1 has a pretty wide confidence interval. So you're not just comparing this and the confidence interval on that with 0 as you're doing in paired t, but you're comparing it against this confidence level interval for the AAD, and that is why it is less significant. So of course the question arises, why bother with unpaired comparisons at all? And as I mentioned, it's not uncommon to see in the literature, people do study designs exactly the way I have it here, and then they report just the paired t's in the 3 groups. They would just say the 2 intervention groups had significant changes in cholesterol, and the control group did not have a significant change, and leave it at that. And I think that's not quite correct. So you have when you look at the change and compare the changes, each subject is their own control, plus you have control for time. If you do the paired test only, you are not controlling for time. And that's the reason you need to have a control group, and you need to do an unpaired t comparing your intervention group with the control. And so just an excuse for me to show this picture of this great statistician. He was so modest, he didn't even use his name. So his name was Gossett, and he wrote his papers as a student. And so the insight from Gossett is that when you work with the standard error of the mean, that is, you're working with a standard deviation and dividing by square root of n to get the standard error, that is actually the standard deviation is from your sample. It's not from the you don't know the true standard deviation of the population. You only have your sample. And so Gossett said, you have to take that uncertainty into account. Because if you repeat this study with a different sample, you will get not only a different mean, but also a different standard deviation estimate. So that was Gossett's work. He said that the t-statistic can't be treated like a z-score, and you have to work out how to get p-values. And the key is that as n increases, Zach made this point a long time ago, as n increases, the standard error goes down. And so there is more confidence in the standard deviation estimate also. So not only does standard error go down, you also have more confidence because you have more subjects on which, in whom, from whom you're calculating the standard error. So there is this idea of degrees of freedom due to Gossett. And so if you had infinite subjects, you can just do like essentially a z-score, 1.96 from the standard deviation. But as your degrees of freedom goes down, the critical value you need for significance goes up. So that means that if instead of lots and lots of subjects, you only have 5 subjects, your critical value has to be 2.6 instead of 2. Now, so my only problem with this is that this doesn't quite deal with the problem that sometimes in small samples, your standard deviation estimate may come out to be an outlier, very small or very big. And so then you may end up with unreliable results. So going back to, I'm not saying go back and look at the thing, that the calculations we did earlier, samples of 4 and 16. So these were the standard deviations we got. But the variability of 4 at a time, you remember those, if you calculate the standard deviations of those, not the mean, but the standard deviations of those 4, those standard deviations vary all over the place. You know, they're supposed to be 15 or 16, but in fact, only some of them are 16. Some of them are there is 30, 51, and one sample of 4 had 73. And then you might have some 4 people who have very unusually low standard deviation. And so that is the concern. But when you have 16, the variation is much less. So I may be losing people here. The point I'm trying to make is that when you have small n, it is possible that your standard deviation might happen to be unusually small. And if that should happen, your calculation would be off. So the t deals with the small n by increasing critical t, but not enough. If by chance a sample standard deviation is half the true value, just by chance, you can see here the standard deviation should be 32, but when you have a sample size of 4, you can range from 16 to 73. So if you happen to have a sample where the standard deviation was 16, you would end up with a false positive result possibly, because your t-statistic would be large. And so it'll artificially double the t with a likely false positive result. So that is a concern that one should have. Okay, so I did this already. Okay, so we're done with the t-test. in Excel. And so the question is, how can we use the third group? And there is really no way to use all three groups, just the way in terms of Excel functions that are offered. So, so just to provide a little bit of rationale for why you may want to use all three groups, even when comparing two groups at a time. The thought is that when we're looking at the difference between two means, and the unpaired t looks at this difference in relation to the standard error. And we already saw how the standard error can be calculated from the standard error in the two groups. But the problem arises, suppose you, instead of two groups, you have four groups, or in this case, three groups. To compare, say, A and B, you would be using the standard deviation that you got in your data with groups A and B. But when you compare C and D, you would be using the standard deviation C and D. But in fact, if you have people randomized into four groups or three groups or whatever, you don't expect the standard deviation to be different from group to group. There are situations, clinical situations, where that happens. But by and large, we assume that the standard deviations are the same in all the groups. So why not do something better than just use the standard deviations in two groups at a time? You know, and the idea there then is to use a pooled standard deviation. You take the standard deviation from all the groups, get a pooled standard deviation, and then compute your t statistic. That is all that is done in an ANOVA. People may have heard the term ANOVA, analysis of variance, and it's not a term that makes any sense at all. And it certainly didn't make sense to me for a long time why it is called ANOVA. But that's what happens in an ANOVA. You say, if you have more than two groups, or as many groups as you have, take the standard deviations within each of those groups and pool them all to get a single pool standard deviation, which you then use for all the t-test-like comparisons. So for instance, again, going back to that HDL change, no, this is HDL change. So if you look at these three groups, what you have is the standard deviations are not quite the same in the three groups. So the standard deviations are 4.3, 3.5, and 2.5. So it turns out step one has a smaller standard deviation than AAD does. Now, if you do a t-test comparing AAD and mono, you're going to be getting 3.92 as a pooled standard deviation between these two. And then for step one, you're going to be pooling these two, 4.3 and 2.5, and getting 3.52. So you have a different pool standard deviation for the mono versus AAD and for the step one versus AAD. And that's going to result in somewhat different p-values, even if you had the same difference between the groups. So it is best to use the same pool standard deviation from, you pool all three and you get 3.51. And you use that to calculate your t-statistic and your p-values and so on. How do we make use of the third group? So we first get a pool standard deviation from all the groups. And as I mentioned before, it's a much better estimate than what you get from two groups. And that is also reflected in an increase in degrees of freedom that I talked about, what Gossett's contribution was. But a big thing for me, a big reason to always do an ANOVA when you have more than two groups, or which uses a full standard deviation, is that outliers become less consequential. Because what happens is that when you have small n in the different groups, an outlier in a group increases the standard deviation of that group. And then what happens is that the t-tests of that group with the other groups become less significant because this outlier has affected not only the mean, but has affected the standard deviation also. So the pool standard deviation lessens. It doesn't get rid of the effect of the outlier. The outlier still influences the mean of that group. But the pool standard deviation at least lessens the effect of the outlier on the standard deviation estimate. So just logically, if you have three groups and two groups are at the same level and the third group is at a different level, you want the comparisons of A with C or B with C to have similar p-values. And if by chance one of them has a different standard deviation, you won't get the same p-value by a t-test. So that's why we want to use a pooled standard deviation. So you have more than two groups, you always have to do an ANOVA and use a pooled standard deviation. Always. And an outlier, as I mentioned, increases standard deviation in its group, affecting simple unpaired t-tests involving that group. Now, the more serious reason is that even people who are not statisticians, when they review a paper, if they see there are more than two groups and the authors say they did t-tests, the reviewer, even a non-statistician, knows enough to say this is no good. Okay. So sometimes the term pairwise comparison is used, which is a little confusing as opposed to paired. But anyway, that's the same as using ANOVA and post hoc t. So maybe I'll do this just to show you. Not something I'm interested in because I'm interested in everybody doing things with R. So I'm just going to go over it very quickly. So, if you go back to that page, biomath.net or info/stat, you see one of the links is there is to do one-way ANOVA post hoc t-test with more than two groups. So if you click on that, you'll be asked to enter how many groups you have, and then you'll be asked to enter your group means and standard deviations and the N. So these are all values you would have from Excel. So we can put those numbers in or copy paste or type the numbers in. If you do all that, you will get these p-values. And we will see that we'll get these same p-values in R when we do a one-way analysis. But anyway, so this is just there for people who are determined not to use R and still want to do a one-way analysis in Excel. Okay, so I'm going to skip this cartoon. Okay, so we're doing pretty well as far as time is concerned, as far as I'm concerned. So I'm done with Excel. So we're going to continue with power analysis. So the power analysis is basically also called sample size calculation. And I think anyone doing any work at all, not just human subjects, but even animal studies, has to justify their study. An important part of the justification is that you're going to have enough subjects, people or animals, so that if what you expect comes about, of course you don't know what's going to happen, but you have certain expectations. If what you expect that the reviewer may agree with comes about, then the number of subjects will be enough to find statistical significance. So that's the point of power analysis. Power, the word power is used to mean that you have sufficient power to find something to be statistically significant, and also called sample size calculation to mean that you say this is the number of subjects or animals I need in order to find my treatment effect or group difference to be statistically significant if things turn out the way I expect, right? So now I have a sort of a simplified approach to power analysis. There is software that you can get that will do power analysis for fancy, all sorts of complex statistical analysis. But I have found that it is possible to do power analysis just for a couple of very basic tests, t-tests and chi-square tests, and that the numbers you get are pretty good, in terms of what you might get if you did a much more complex analysis. So I have basically 3 approaches to power analysis, and so I will go through them. And I think very broadly, any power analysis you do yourself will sort of fall under one of these 3. And then within that, you will, in my view, you can do a t-test or a chi-square test, and that will be enough. And after we do the basic power analysis, I will also talk about equivalence and non-inferiority. The usual power analysis is for superiority. That is superiority meaning difference. Maybe superiority is a bad word. That is, you expect the 2 groups to be different, or you expect the 2 treatments to be different. So maybe I should say design for difference, not superiority. Okay. So as I mentioned, power analysis is also called sample size determination. So you can have a prospective situation where you say, how many do I need to study so that I get a significant p-value? And a retrospective study would be, I'm going to do a retrospective study. I know how many subjects I have. Will that be enough to find statistical significance? So as I mentioned, so 3 approaches. So the first approach, which I think is the most common approach, is you have an expected difference between the groups or a treatment effect. So now you calculate the number of subjects to be studied so that if the groups truly differ by their expected value, not that you will actually get that expected value, but if the true effect is that, then there will be statistical significance most of the time. Of course, there is no guarantee in real life because you might have outliers, you might have other issues. So most of the time, that is, we say the typical power setting is 80%. That means 80% of the time, if the groups truly differ by the expected value, I will get data that will in fact be statistically significant. So that's approach 1. A second approach is you don't know what to expect, but you really want that to be at least a certain amount for it to be interesting. Maybe this treatment is expensive or taxing. So, like if you're promoting a new diet, maybe the diet requires a significant change in people's lifestyle. So you may specify the least significant difference of clinical interest. You could say, the treatment has to have at least this much effect. So what you may do now is calculate how many subjects you need to study so that there will be statistical significance if the true difference is at least this least significant difference. It's very similar to approach 1. The only difference is in approach 1, you have some hope, some expectation of what to expect. Here, you're saying, I really want it to be at least this much. And that's what this design is. Now, the third approach is different from the first two. Here you say, if the number of subjects is fixed and known, as in a retrospective study, or prospectively with limited resource, right? I mean, because even a prospective study, like, I have residents here, and, some of them are planning to do prospective studies, but they only have a limited time to do the study. They have to finish the study before they finish the residency program. They also have limited time every week to do their elective research work. So you have limited resources, or there are financial constraints, whatever. So if the number of subjects is fixed, either because it's retrospective or because you have a limited budget going forward, you can calculate the smallest difference or treatment effect for which the available number of subjects, as before, will lead at chosen power to statistical significance. So I hope people see that this is sort of looking at it backwards. That is, we are not calculating the number of subjects. The number of subjects is fixed. Rather, we are calculating what is the smallest difference that you have the power to find significant. Okay. So as I mentioned before, we're going to do power analysis just for 2 tests, basically. For continuous data, learn for t-test, and for categorical data, for chi-squared test. I mean, our webpage also does it for correlations and one sample test, but I won't get into those here. So, but the point here, the key point though, is that any other problem simplify to a t-test or a chi-squared. So, for instance, one resident I have this time, she's doing a project where there are multiple risk factors that are going to be analyzed finally in a logistic regression. We're going to do a logistic regression at R in a couple of weeks, but before doing the logistic regression, before collecting the data, there is a reasonable question: is there hope for the study? So there, my suggestion to her is to do power analysis for just one factor at a time. Ultimately, you're going to do a logistic regression, taking all factors into account. But for the power analysis, you just look at one continuous factor, maybe one categorical factor, and ask, do I have the power with this many subjects? Okay. So just a couple of comments, to say what does it mean to simplify to a T or chi-squared? Suppose you're actually planning an ANOVA with multiple groups, post-hoc contrast. So you power for a t-test, comparing the groups expected to be closest. We'll see an example of that when we work things out. So you're doing the power analysis for a t-test. You're actually going to do an ANOVA finally. But for the power analysis, you just do a t-test. Or you may be planning to do a non-parametric analysis. Not parametric analysis at all, because you're looking at, say, length of stay or viral load or something, which are going to be analyzed non-parametric. So my approach is, again, not the final analysis, but the power analysis you do for a t-test. And, take the median, the expected median to be the mean, and the standard deviation to be something from the interquartile range. Or suppose, as I mentioned before with my resident, you're planning a logistic regression, so you just do separately for each predictor of interest. And And then, or suppose you're doing a Kaplan-Meier. We'll get to Kaplan-Meier in a couple of weeks. So one point that I didn't make so far, I should stress it more. There is a key difference between power analysis and the final statistical analysis. The final statistical analysis, you want to do everything carefully, do the test, the appropriate test, and report the exact p-value that you get. The power analysis is different because you're just planning a study and you want a rough idea of how many subjects to study. It's not that the power analysis says you need 27 subjects and then you're going to say, it really matters to me, 27 or 26. No, this is an approximate figure because we'll see momentarily that 27 may seem exact, but it is actually based on assumptions that you're providing to the calculator. So if you change your assumption a little bit, that number will change as well. So that's why I'm not so hung up on doing the power analysis for the actual final analysis that's going to be done. Okay, so we'll see this right away here. So like for an unpaired t-test, an approximate formula is the number of subjects in each group is 16 times the standard deviation squared over the effect squared. So this is circular because the whole point of the study is to find delta. But this formula says you have to take a stab at the delta to get the n. And there is no way around it. You have to live with it. So you have to start with some idea of the effect size to find n. That's just how it is. I would like you to go to this web page in your browser. I think, I don't know if I mentioned it last week or not, both the stat, the biomed.net/stat and /power, both of them can be done on your telephone. There is no need for a computer to do these calculations. You can just, in fact, I do that when I'm in a seminar and somebody is showing something and I get a little dubious about what they're saying. I'll just go to one of these two pages and check for myself if what the speaker is saying makes sense or not. So anyway, so we're going to a slightly different page here. Not instead of stat, you need to type power. Okay, so we're going to start by repeating the power analysis for the t-test that we did today. So the standard deviation of the total cholesterol change was about 14 milligrams per deciliter. And on the mono diet, TC dropped by 20 milligrams per deciliter. So suppose you'd say, I want to repeat this study. This study was done 30 years ago. I want to repeat this study. How many subjects do I need? If this is my goal, to show that a drop of 20 milligrams per deciliter is significant. So going back to the basic thing, we are doing t-tests. And then in terms of approaches, we're going with the first approach because we have an expected difference at 20 milligrams per deciliter to drop. So that's what we're doing. So what I would like you to do on that page, the power page, click on t-tests on group meets and go. And when you do that, you'll get to a page. We'll work on the left side of the page. So you put in numbers here, and or you can just put the difference that you expect. So we expect no change in the AAD, and we expect a 20 drop in the mono group. And you click on result. Oh, I'm sorry, you have to put down 14 for the standard deviation. And when you click on result, you should get 9 subjects in each group. So that's it, really. So if you know what to expect and you have an idea of the standard deviation, that's it. Okay. Now, it is possible that when you're repeating this study, maybe the standard deviation won't come out to be so small. For one thing, we fed our students all the meals, and they all lived in the dorm. They're all, very narrow age range. And so maybe the repeat study, you can't expect the same small standard deviation. So you say, well, what if the standard deviation is 50% bigger? That is, instead of 14, maybe it's 22. So we keep these two the same, and we change this to 22. So when you do that, you find you need 20 subjects, not 9. So this again, to reinforce in you why these calculations don't have to be so precise, because you don't actually know what the standard deviation is going to be. So when if it is 14, you need 9 subjects. If it is 22, you need 20 subjects. But that's something you have to live with. The power analysis requires you to guess what these quantities are. Okay. Now, suppose I'm repeating this study now. I'm repeating this maybe in the general community, where I give dietary advice and maybe ingredients, but not also all the meals and so on. And I can't expect the same 20 milligram drop in this study. However, as a public health measure, it'll be great if everybody's cholesterol level simply went down by 5 milligrams per deciliter. Doesn't have to go down by 20. If it goes down by even 5, it's great for me. I'm okay if there is only a 5 milligram per deciliter. I want to find that to be significant. So this is the second approach. You're able to specify the least significant difference, and you calculate the number of subjects. So we go back to this, and this time I think I'm going to enter slightly differently. So I'm going to enter 5 here. You can enter 0 and 5, or you can just enter 5 here and 14 here. If you change this to 22, you should change it back to 14. And when you do that, you get that you need 125 subjects. So you can see that this is a big change here now. That when the effect you're looking for goes from 20 to 5, the number of subjects you need shoots up from 9 to 125. And this is complete to be expected from the math. You may or may not remember the approximate formula involves delta squared in the denominator. So when delta is 20, you get something. If you make the delta to be 5, that means the number of subjects needed is going to be like 16 times. So 4 squared. So that's what is happening here. The number of subjects goes up. And now on top of that, if you say, I don't know whether it'll be 14 in the general community, maybe it'll be a bigger variation. So if you make that 22, that 125 goes up further to 305. So you can see here we have just 9 subjects needed if the numbers to be expected are the same as we had in our New England Journal paper. But if we say conditions are different in one way or another, so that the what I want to design for is smaller and the standard deviation may be larger, so the number of subjects needed goes up a lot. So that's so I'm done with t-test now, and we're going to do for a chi-squared next. So this is a famous paper. It did not get the credit that it should have received at that time. So this was the first randomized trial to see whether postmenopausal hormone replacement was beneficial to the heart or not. So, and there's a background that I won't go into. This was actually funded by the company, drug company, because they thought if they did this trial, they could get FDA approval for HRT to be prescribed to all postmenopausal women, not just women with symptoms. Study was done very properly, even though it was funded by the drug company. So about 2,800 women were studied. So I want to look at the method section and see how we can calculate the power for that. So the basic point was they expected a certain event rate in the placebo group, which actually was 13%. There was a 13% event rate in the placebo group. Some composite outcome, 13% of the women experienced one of those events. And they expected a 24% reduction in the women on HRT. Of course, in point of fact, there was no reduction. There was no benefit at all. But this was the expectation. And so they expected the 13% to drop to 10% in the HRT group. So the question then is, how many subjects would they need under these assumptions? So going back to my early slide, so we're just doing one of two tests. So this time it's a chi-squared test because we are comparing proportions. What proportion of women in one group had an event compared to the other group. And this is back to the first approach. There's an expected difference between the two groups, and we calculate the number of subjects. Okay. And so 13% on placebo and 10% on HRT. So you go back, I think you can click on do another design on the t-test page, or just go back in the browser, and I want you to pick chi-square test on the right side. You know, two groups, chi-square test on proportion. And if you do that, this is what you should get on the left side of the page. You enter the two proportions and you click result. So the only thing is, the way we have our web page set up, you have to enter the proportions as decimals, not as percentage. So you need to enter it as 0.13 and 0.1. So when you do that, you get that you need about 1,800 subjects in each group. And so that is roughly the number of subjects they actually used in their study, about 3,500 subjects total. And anyway, but this is just to, I'm not saying this is how they did the power analysis, but this is just to show how one may approach power analysis with proportions. Okay, so I'm going to do one more, and then and we'll quit after that because I want to explore the third approach here as well. And so this was a, seemingly silly study where they tried to see whether prayer was effective in reducing complications in post-bypass surgery. And this was the study was done at a time when maybe even now there are people who believe in the power of prayer, but anyway, they actually were able to get funded for this research. So in this case, they said they judged certain things to be clinically important, and they calculated, they expected certain event rate, but there were three groups. I don't want to get into why they had three groups, but they had three groups, and these were the expected proportions: 45%, 55%, and 35%. And they wanted to figure out how many, so we want to figure out how many subjects. They claimed that those were the smallest differences that would be clinically important. So we're going to take that approach. Second approach, least significant difference, and calculate the number of subjects. And so now we're going to work on the left side still. And now the thing is that there is a control group where the event rate was 55%, they expected 45% in one group and 35% in the other intervention group. So now a couple of things come up. One is, which one should you design for? You design for the smaller difference, right? I hope it's clear to people that the number of subjects you will need to compare these two is going to be larger than the number of subjects you need to compare 55 to 35. So it makes sense to design for the smaller difference. So that is clear. Also, they said that they wanted to control for the fact that they were doing two comparisons. So you can do a little bit of that in our web page by changing the alpha. You can, it's the default is 0.05. We don't offer any value at all. We offer a few possibilities. So 0.02 is a possibility. So let's use 0.02 and then put in 0.55 and 0.45. And when you do that, you get about 500 subjects needed in each group. And that's roughly what the numbers that they use in their study. So is this clear? And final point, I think this will be my last bit. Suppose the resources allow only 200 subjects in each group. That is, they don't have the money to study 1,500 subjects. They can only study 600 subjects. How small an effect could they detect with 200 in each group? So now we are finally coming to the third approach. Number of subjects is fixed. Not a retrospective study, but prospective with limited resources. So now we don't say what we expect to see, but rather we calculate what sort of difference we can find significant. So now you work on the right side. We're still on the same page, but you work on the right side and you say, I have 200 subjects in group 1, and so what can I expect to see? So you put 200 and 0.55, and this is what you should get. Now, the reason you don't have one answer, you have two answers here. So the reason you have two answers here is that our web page doesn't know whether you expect group 2 to have a smaller event rate or a higher event rate. And so we go with this one because, we go with the 0.39. And that's the reason the program gives two P2s, because we don't know which proportion you are interested in. So you don't use both of them. I can't imagine. So you go with the one you expect your group 2 to be in. So you hear they have a prayer intervention, so they expect lower event rate, so you go with that. So what this means is that if they had only 200 in each group, they can find significance only if the groups differ not by 10%, but by 15%. Right? Instead of going from 55 to 45, you'd have to go from 55 to 39 to have power to find significance. I'm going to stop here. We are next going to explore the effect of changing relative numbers in the two groups. So I think this is a reasonable place to stop.